Okay, so forgive me for being really tired. I am really tired. I've had a very busy day. But I wanted to knock this presentation out. It's pretty short and it covers asynchronous counters with MSI gates. So if you remember, MSI stands for medium scale integration. And pretty much what that means is instead of designing your counter with a bunch of flip-flops, you can actually purchase one IC, that's integrated circuit, little black chip, that will function as an asynchronous counter. So I think right off you can see where there's a benefit to being able to do that. So this presentation, and I'm just realizing now that I seem to have reverted to the old version of PowerPoint because everything is where it was before last weekend. That's really weird. So anyway, the presentation topics are to introduce the actual IC chip. It's a 74LS93 as a 4-bit ripple counter. Remember, ripple counter is an asynchronous counter. Look at the block diagram and the connection diagram, clock sequence, like basically the manufacturer information on this particular IC and what it does. Then provide an example and then discuss like when would you want to use this in a design, when would this be advantageous. And it is a pretty short presentation. It's only 9 slides. I have a little bit that I want to add to it just as we're going through it, but not much. It's a very, very straightforward presentation. So this is the block diagram for it. And honestly, I find this a little bit convoluted. Like they have the divide by 2 section and the divide by 8 section. To me, like a better way of thinking of that is like you've got like a 1-bit counter. Let me turn the laser pointer thing on. Okay. Like a 1-bit counter and a 3-bit counter that can be connected to give you a 4-bit counter, but they can also be leveraged separately. Divide by 2 and divide by 8 just seems like a very weird way to put that. Each section is triggered by a high to low transition on the clock inputs, and they can be used separately or tied together. So again, you can use it as a 1-bit counter, a 3-bit counter, or you can connect them together and get yourself a 4-bit counter. But they have the separate clock triggers, and of course, like high to low is that negative edge on the clock. The counts have a 2-input gated master reset that is a clear that's down here. And this is like a little note here that becomes important if you wanted to use it, that the JK inputs are connected to 5 volts. And what they did is they didn't put that in the block diagram just because it made it cluttery. So it was easier just to say your JK inputs were both set to 5 volts, which means that they are in toggle mode. So when J and K are both high, it just means that the flip-flops are set to toggle, which is what you want them to do if you're using them in a counter. So that's the block diagram, and pretty much all of that would be in one chip. So instead of you wiring a bunch of flip-flops together to create a counter, you can buy the 74LS93 and that will do it for you. This is how you cascade them. So the 1-bit counter and the 3-bit counter down here can be connected together. They can essentially, that's cascaded together to make a 4-bit counter between QA and input B, but you have to do a separate connection. So if you wanted to use this as a 4-bit counter, this would actually be done with an external wire. So you would have to take the output QA and actually wire it into the clock input for the second part of the counter, and you would have to, like, you the engineer would have to make that wiring if you wanted to cascade them together. So that was like one little like point that needed to be made about this, and they highlighted it in blue. So if that is something that you're going to do for your activity, you're going to create a ripple counter, you're going to need to do that wiring. They provide you with the schematic, but it is important that you're not just copying the schematic, you are like paying attention to what is wired where on the chip. All right, then this is, we got the block diagram. This is the connection diagram. We've looked at those before because we haven't done a lot of breadboarding because we didn't get our supplies, and breadboarding takes a lot of time and it's just hard. Maybe after you guys take your EOC or something, we'll back up and we'll do some breadboarding, or we'll explore with the breadboards. But notice a couple of things to notice. We get used to like ground and 5 volts being on like pins 14 and 7 or 1 and 8. Like we get used to those being at opposite ends, but notice that your ground is on pin 10 and your VCC is on pin 5. So that's just important to know. And then you use the block diagram to figure out like what it is you were going to do. Now, remember, if you wanted to cascade them, you would have to take QA and wire it into the clock, which would be input B. And so you would have to physically take this wire for QA and put it into input B, which is over here. So you'd have to take a wire and wire that up on your actual chip. Okay. So that's make sure you do that. Okay, next thing, this is like your clock count. That's pretty ordinary. 0 is low, 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 0, 0, 0, 0. 15 is 1, 1, 1, 1. And then you have everything in between. Just, note that QA is your 1's bit and QB is your 2's bit, your 4's bit, and your 8's bit out here. So, and then this is important to note. You've got that gated reset, and notice that it resets when both resets are tied high. So this becomes important on the next slide. They show you an example, but you kind of need to notice what your resets are tied to. So as long as either of your resets are low, the chip is going to count for you. If both of them go high, then that's when you're going to reset back to 0, 0, 0, 0. If you only want one reset to trigger it, which they do in the particular diagram in this lesson, what you would do is tie one of your resets high. So tie one of them high, and then the other one will sit low, and then when you want to reset it, you just have to set the one of them high, because the other one will be tied high, so that you wouldn't want the other one to float, because floating does weird things. So here's an example, one, and they did say like they were going to do an example. It's going to be a really short video and lesson, which is fine. I don't think you guys object to that at all. So this is the counter. Notice the external wire on here. So you do take the output from QA and wire it into input B. That's what's necessary in order to turn this into a 4-bit counter. This one we want to reset at 12, which is 1100. So remember that to get the 12 to appear, the actual trigger needs to be on the 13, which is 1101. So this would be the 1. Notice that this is not inverted 1. The one that we want to be 0. Okay, we want this to actually be 0, so we're going to run it through the inverters so that will be a 1 on the other side of the inverter, and then 1. So there's your 1101. All of these would be positive. You're going to run them into the NAND gate, which is going to NAND them and then turn them low, because it's NAND. It's going to AND them and then turn them low. This I find, yeah, because the NAND is inverting it, and then we're immediately running it through an inverter again. So the NAND, so these are all high. This right here is going to make it low, and then running it through another inverter is going to make it high again. And then notice the 2 resets. So this goes back to what I was saying earlier. The first reset is tied to 5 volts, but it's when they're both high that the counter will actually reset. So you take one of your resets, tie it to high, and then this will be high, then low, and then high again. And then when this one goes high, then they're both high, and it's going to take all your outputs and reset them to 0, 0, 0. Now, if you have control over this, you clearly don't have to negate and then negate again. That's a waste of a gate and a chip. So an AND gate would serve that purpose, if you're able to if you're able to do it. And this is the timing diagram for that. So you can just see how it counts: 0, 1, 2, 3, 4, 5. And then here's your 1100. That's your 12 or your hexadecimal C. And then it's going to run through the combinational logic right here, reset it, and it's going to go back to 0, 0, 0, 0. And then just notice the timing diagram. You've got your 1's bit, your 2's, your 4's, and your 8's. So that's your example timing diagram for that circuit there. And then this is like our limitation. So as with most MSI integrated circuits, there's a trade-off for the convenience, because now you have everything you need. It's just going to count in one chip as opposed to building your counter with all the flip-flops. The trade-off with the convenience is the lack of design flexibility. So that integrated circuit is only going to do one specific thing. So this is where they get into some of the limitations of the 74LS93. So this lack of flexibility can lead to limitation or inability to use it in certain applications. So for example, the flip-flops are not presettable, thus the count must always start at 0. So in the last activity, I had you modify a circuit so that it started at 1. If you were using this particular chip, you wouldn't be able to do that. And then as designed, it can only be used to implement up counts. So if you need a down counter or you need some kind of counter that can be modified to go from up to down, you wouldn't be able to use this IC. But if your design calls for an up counter that starts at 0, this is ideal. This is going to get you where you need to go without going through all the trouble of using the flip-flops. So that was the entire presentation. We got it in under 12 minutes, so pretty good for a very exhausting Saturday. And so what you're going to do for the activity for this is you build one circuit and make sure that it works, and then you modify it, I think is how, but I'll give you the details in class about exactly what I want you to turn in for that. And then the next thing we're do is we're going to do a project where you're going to design a counter for like serving people like in a deli, that will be able to go up with the flick of a switch, but will reset under particular circumstances. So this is going to lead into probably a multi-day project, and then we'll go into synchronous counters after that.